In this video, we're going to do even more with derivatives and combine calculus with one of our favorite things in the whole world, which is, of course, word problems. So today we're going to do related rates problems, which use derivatives to find the rate at which one variable is changing using information about another variable. You're going to need to know how to do implicit differentiation to handle these problems. So if you need a refresher on that, go back to the implicit differentiation video. It's a few videos back, and then come back to this one. So related rates problems. The first thing you're going to have to do on these problems is find an equation that relates the two quantities in your problem. Or sometimes more than two quantities. And then step 2 is to use the chain rule or implicit differentiation to differentiate both sides of your equation with respect to time. Then you will need to solve for the rate that you're asked to find using the information given to you in the problem. Now, on a lot of related rates problems, it helps to first draw a picture to illustrate what's going on, just to help you figure out what your equation is. A lot of the equations actually come from geometry, so you should make sure you're good on all of your volume formulas, the Pythagorean theorem, things like that. So let's start right away with an example. The rest of this video is just examples of various related rates problems. So our first example, we have air is being pumped into a spherical balloon. So that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius increasing when the diameter is 50 centimeters? All right, so before we actually solve this problem, let's just take a look at what they even tell us. They give you a big hint right here with this volume that tells you we're going to need the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. So we're definitely going to need that equation. Notice that already gives us an equation that relates our volume and our radius, which is good. Those are the two things we have information about. Now, what is this rate of 100 cubic centimeters per second? Well, when you see a rate, that is referring to a derivative with respect to time. So this is dv dt. It is 100 cubic centimeters per second. The thing we're trying to find is how fast the radius is increasing when our diameter is 50. So I'm just going to write down some things that we know. We know that dv dt is 100. Something that we want is dr dt when our diameter is 50. Well, the diameter being 50 means my radius is going to be 25. The only reason I'm converting that to the radius is because our function, or our equation here, relates volume and radius. It doesn't have a diameter in it, so I converted it into the variable I'm actually going to use. So we have actually everything we need to do this problem right here. I'm going to rewrite the things we know and the things we want, and then we're going to solve this using implicit differentiation. So the things that we know that volume is 4/3 pi r cubed, and we know that dV dt is 100. What we want is dr dt when our radius is 25. So the way we solve these problems is you use implicit differentiation to take the derivative of both sides of your equation. So I have v equals 4/3 pi r cubed. Take the derivative of both sides with respect to time. dV dt equals, my 4/3 pi is a constant. My power rule says this 3 is going to come down and multiply. That will cancel out the third. I get 4 pi r squared, and then we need to multiply by dr dt because we're taking the derivative with respect to time. Now that all the derivatives are done, we just have to plug in all of the information that we know. And you should be able to plug in stuff for everything except for the thing we're solving for. My dV dt I know is 100, so I can put a 100 over here on the left side. I know my r is supposed to be 25. And now I have something that I can solve for dr dt. So if I divide both sides of the equation by 4 pi times 25 squared, I'm going to get 100 divided by 4 pi times 25 squared. That is my dr dt, which we can simplify a little bit. 100 is 4 times 25, so I can cancel out the 4 and one of the 25s and get 1 over 25 pi. And my units for this problem were in centimeters per second. That is the rate that the radius is increasing. So the radius is growing at a rate of 1 over 25 pi centimeters every single second while we're pumping air into this balloon. And there we go. We just survived our first related rates problem. So these problems, really the hardest thing is getting them set up. Once you have the equation you need, it's just a matter of doing implicit differentiation and plugging in your information. So let's do another example. This example involves a ladder. We have a ladder that is 10 feet long, rests against a vertical wall, and if the bottom of the ladder slides away from the wall, at a rate of 1 foot per second, how fast is the top of the ladder sliding down when the bottom is 6 feet away? All right, So I left that space over there so we can draw a picture and kind of figure out what's going on in this problem. So what we have is a vertical wall with a ladder leaning against it. My ladder is 10 feet long, and the ladder is forming this hypotenuse of a right triangle. I'm going to just call this side of the triangle y and this side x. So what do I know? Well, we all know the Pythagorean theorem. That's a way to relate some of these sides. We know that x squared plus y squared is going to be 10 squared, which is 100. That's always going to be true. Something else that we know is the rate at which the bottom of the ladder is sliding. So here's my rate. Remember, a rate tells you it's a derivative. If x is standing for the bottom of the ladder, the distance that the bottom of the ladder is away from the wall, then I know that dx dt is 1 foot per second. And then all we have to do is figure out what it is we're trying to find. We want to know how fast the top of the ladder is sliding down the wall. That's going to be my dy dt. And then I'll just have to plug a bunch of stuff in. So let me erase all of the words. And we will set up the whole problem and solve it. So again, here's the picture in case you need it. Y, x, this is 10. Things that we know is x squared plus y squared equals 100 from our Pythagorean theorem. We also know that dx dt is 1 foot per second. And what do we want to find? We want to know what dy dt is when the bottom of the ladder is 6 feet away. So when x equals 6. Now notice, if I take my equation and do derivatives of it, I'm going to have a y that I need as well. We don't know y right now, but we can figure out y. So I'm just going to give myself a little note here. When x is equal to 6, we'll have 6 squared plus y squared equals 100. And that means that y ends up being 8. You would do 100 minus 36 to get 64. Take a square root, and y is going to be 8 at that point. So now we're all set to solve. Take your equation that relates everything and take a derivative of both sides with respect to t. I get 2x dx dt plus 2y dy dt equals 0. And now I just plug in everything I know and solve for the thing that I want. I know my x is supposed to be 6. My dx dt is 1. We already found y is going to be 8. And this is what I have to solve now to figure out what dy dt is. So now that everything is all plugged in, it's just some arithmetic to get it figured out. I have 12 plus 16 dy dt equals 0. So that means 16 dy dt is negative 12. And then I just have to divide by 16. And when I reduce that fraction, I get negative 3 over 4. And it's negative 3 over 4 feet per second. And what this means is that the top of the ladder is sliding down the wall at a rate of negative 3/4 feet every single second at that particular instant in time. All right. So now we've done a problem that involves a volume, and we've also done one using the Pythagorean theorem. There are other types of problems, of course. In fact, our next one is also going to use volume, but it's going to be volume of a cone, and it's a little more complicated than the ones we've done so far. So we have a water tank. And this water tank has a shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank, at a rate of 2 cubic meters per second, find the rate at which the water level is rising when it is 3 feet deep. All right, so before we erase all of the words, let's just draw a picture kind of saying what's going on here. This inverted circular cone just means we have a cone that looks like this. I'm going to have water inside the cone. I know that the radius of the base is 2 and the height is 4, but I'm also going to have a radius of the water and a height of the water. And what is the volume of a cone? Well, volume of a cone is 1/3 pi r squared h. And let's take a look in this problem. What are the things we know? And we'll write it down after I erase everything. But things that I know is, I know that water is being pumped in at a rate of 2 cubic meters per second. That's going to be dV dt. The volume is changing at a rate of 2 cubic meters per second. The thing that I want to find is dH dt, how the height of this water level is changing when my height is 3 feet deep. Notice that we know nothing about the radius of the water, but we'll figure that out using geometry. So let's write down everything we know and everything we want to find and try to interpret how to do this problem. So again, here's my picture. Here's a height of 4. Radius of the tank is 2. I know I have a water level in here that has a radius r and a height h. Things that I know, volume is 1/3 pi r squared h, and I know dV dt is equal to 2 cubic meters per minute. What I want is dH dt, how fast the height is changing, when the height of the water is 3 meters, because it said the water was 3 meters deep. The only problem with this situation right now is that this volume equation involves our radius and our height, and I have 0 information about the radius, r, or dr dt, so I would be in trouble here doing this. But luckily, we have geometry to help us. I'm going to simplify this picture. Instead of looking at it as a cone, just look at the triangles. So I have a triangle here that's 2 and height 4. That's the triangle formed using the outside of the cone. And then I have another triangle in here that has a height and a radius like that. We have similar triangles. Using geometry of similar triangles, I know the ratio 2/4 has to equal my ratio of r over h. And this means that I can solve for r in terms of h. Then I can rewrite my equation so it only has h's in it because all the info I know involves h. If I solve this for r, I get that 1/2 of h is equal to r. So that means that my volume equation can be rewritten as 1/3 pi times 1/2 h squared times h. And I can simplify that. Then I will have a volume equation that only involves h's, and then I'm good to go to take all my derivatives. So let's go ahead and simplify this volume. 1/2 h squared would be 1/4 times h squared. The 1/3 times the 1/4 gets me 1/12. So I can rewrite my volume equation as 1/12 pi h to the 3rd power. And now I'm ready to do my derivatives. Everything else is staying exactly the same. So, if I take a derivative of this guy, I have v equals 1/12 pi h to the 3rd. Derivative of both sides, I get dv dt equals, we're going to have a power rule here. When the 3 comes down, multiplies to get 1/4 pi h squared dh dt. And now I'm ready to plug in all of my information. dv dt is equal to 2. My h is 3. And now I can solve that for my dh dt. So what I have at this point is 2 is equal to 9 pi over 4 dh dt. So when I solve for dh dt, I get 8 over 9 pi is dh dt. And I should include my units. This is 8 over 9 pi meters per minute. And that is the rate at which the height of this water is changing when we're pumping all this water into the tank. So, like all related rates problems, the hardest part of these is the setup and remembering all of your geometry and things to get it set up. Once it's set up, it's just a little bit of implicit differentiation and plugging your information in. Okay, let's do 2 more related rates examples to finish the video up. So car A is traveling west at 50 miles per hour. And car B is traveling north at 60 miles per hour. Both cars are headed to the intersection of the roads. At what rate are the cars approaching each other? When car A is 0.3 miles away from the intersection, and car B is 0.4 miles away. So before we erase all the words and set it up, let's kind of analyze what's going on here. So I'm having one car traveling west and the other one traveling north, and they're heading towards an intersection. So traveling west would be going this way, and traveling north would be going this way. So they're meeting each other like this, making a right triangle. The distance between the cars would be the hypotenuse of the triangle. So we're going to be setting up a right triangle, which means we're probably going to use the Pythagorean theorem. Now, it doesn't tell us specific rates using the word rate in this, but we do know our rates are our miles per hour. So I know that dA dt is 50 and dB dt is 60. What I'm trying to find is the rate at which the hypotenuse is changing when these cars are certain distances away. So let's go ahead and draw our picture and write down what we know and what we're trying to find. So here's our picture. We have the intersection of the roads right up here. I have car A going this way and car B going this way. And I'm going to call this other side C. And that side C is going to actually be the distance between the cars. So things that I know my Pythagorean theorem, a squared plus b squared equals c squared. I also know that dA dt was equal to 50 miles per hour, and dB dt was equal to 60 miles per hour. What is it that I want in this problem? I want to find dC dt, the rate at which the two cars are getting closer together when A was equal to 0.3 and B was equal to 0.4, the distances away from the intersection. So take a look at the equation that we have, the a squared plus b squared equals c squared. All right, well for that, once I take all of my derivatives, I'm still going to have a's, b's, and c's, as well as dA dt, dB dt, and dC dt. The only thing I don't have information about right now is what c is going to be, but we can find that. Let's find our c first before we do all of our derivatives. When a is 0.3 and b is 0.4, I know that I'm going to have 0.3 squared plus 0.4 squared equals c squared. And this, of course, is going to be 0.09 plus 0.16, which is 0.25 is c squared. Take a square root to get c equals 0.5. So now I'll be all set to take derivatives and I have everything I need to plug in. So I had a squared plus b squared equals c squared. When I take my derivatives with respect to time, I get 2a dA dt plus 2b dB dt equals 2c dC dt. And now I can just plug in everything that I know and solve for dC dt. I know my a was 0.3, my dA dt was 50. My b is 0.4 and dB dt was 60. And I know my c is 0.5. So notice on this right side, we have 2 times 1/2, which is just 1. So I already have dC dt all by itself. And then this 2 times 0.3 times 50, that is equal to 30. And 2 plus point, or 2 times 0.4 times 60, that is equal to 48. So I end up getting 78 miles per hour is the rate at which the cars are approaching each other. Not too bad. I actually really like the ones with the Pythagorean theorem. They seem much more straightforward to solve. I feel like students tend to be more comfortable with those problems as well. All right, so far, all of the things that we've done have involved volume or the Pythagorean theorem. We need to do one that involves trigonometry to make sure we don't forget that trig can show up in all of our calculus problems. So let's finish with one example using trig, and then we'll be finished with our related rates video. So an example, a man walks along a straight path at a speed of 4 feet per second. A searchlight is on the ground 20 feet from the path, and is kept focused on the man. At what rate is the searchlight rotating? When the man is 15 feet from the point on the path closest to the light. All right, so I'm going to draw a picture representing this over in that corner there, and then we'll set it all up. So we have a man walking along a path, straight path. We're going to say he's going this direction. Then 20 feet away from the path, we have a searchlight. There's my searchlight, and it's going to be focused at the man, and it rotates as the man gets closer. So I'm going to call this angle here theta, and I'll call the distance the man is away from this point here, I'll call that distance x. So we know a few things. We know that dx dt, the rate of the man, is 4 feet per second. I know this distance is 20, and I'm trying to find the rate at which this angle is changing. That's my rotation. So I want d theta dt when my x happens to be equal to 15. So let's go ahead and redraw the picture and try to find an equation that will work so that we can find our d theta dt. So here's my picture again. X, we have theta, and this was 20. So first, let's try to figure out an equation relating theta and x. Well, using all of my trig that I know, the tangent of theta is going to be x over 20. So things that I know, tangent of theta is x over 20. I also know dx dt was equal to 4. The thing that I want to find is d theta dt when x equals 15. So let's go ahead and just see what happens when we try to take the derivative, and see if we need to figure out any more information. So if I take my derivative of tangent theta equals x over 20, my derivative of tangent is secant squared, and then I have d theta dt equals the derivative of x over 20 is 1 over 20, and I have dx dt. Well, we do see one slight issue. I know what dx dt is, but I don't know what theta is, let alone secant squared of theta. But we can find that secant squared of theta. So what we need to do is find what secant squared of theta is to finish the problem. So I know we're trying to find this when my x is equal to 15. So what is this side of this triangle? Well, I know 15 squared plus 20 squared is going to equal that other side squared. So what I have over there is that that other side, my hypotenuse, ends up equaling 25. You'll get this combined together is 625. You take the square root to get 25. So this side of my triangle at the point of time I care about is 25. I want secant squared of theta. Well, what's secant of theta? Secant of theta is the same thing as 1 over cosine of theta. Cosine is your adjacent over the hypotenuse. So 1 over cosine will be hypotenuse over the adjacent. So this means that my secant of theta is the hypotenuse, which is 25, over the adjacent side, which is 20, and that simplifies to 5 over 4. All right, so now I'm ready to actually solve for what I need to find. Where we were at, we had taken our derivative and we had secant squared of theta, d theta dt, is equal to 1 over 20 dx dt. I now know secant of theta is 5/4. So I have 5/4 squared d theta dt equals 1 over 20, and my dx dt was 4. So let's simplify. 5 over 4 squared is 25 over 16. I have d theta dt equals 4 times 1 over 20 is 1/5. So this means that d theta dt is equal to 1/5 times 16 over 25, which when I multiply those together, I get 16 over 125 radians per second. So the angle is rotating at 16 over 125 radians per second. That tells us how quickly the searchlight is turning to keep focused on this man. All right, so that's all I got for you for today on related rates. Again, the hardest part of related rates is getting the problem set up. You need to be comfortable with your trig and with basic geometric formulas in order to get problems set up for most of the problems. After it's set up, take implicit derivatives, plug in everything you know, solve for what you need. If you have any questions, feel free to drop them below. Or if you're a current student, you can email me your questions or attend my office hours, and I'd be more than happy to help you. I'll see you in the next video.